Okay, so now what we're going to do is we're going to prove the Pythagoras theorem using similarity. Okay, so just to remind you what we just learned, that, okay, if triangles are equiangular, they are similar. Okay, so if we want to show that two triangles are similar, and we want to use that ratio of their sides business, we first have to show that they are equiangular. We have to show angle, angle, angle. So in the same way that we would show using side, side, side that they are congruent, to show that they are similar, and therefore we can use this ratio business, we'd show that they have three angles that are equal. Okay, so what we're going to do is we're going to now prove Pythagoras' theorem using this similarity. Now, to prove Pythagoras' theorem, there's more than 100 ways to do it. Probably much more than that. You can prove Pythagoras in many, 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 many different ways. This is just one way. And this is also quite a complicated one, but and there are easier proofs for Pythagoras, but it's just to help you use similarity and show you how powerful it is. So Pythagoras' theorem says that we've got a right angled triangle, okay, and in a right angled triangle, if I take the right hand sides and I add this sum of their squares, it means I square each side of the right angles, and I add them together, then I'll get the hypotenuse square, AC square. And we're going to use similarity to prove that that is true. Okay, so again, I'm going to show you more or less the outline, and as soon as we have the outline, that's all you need to go and study is what's the outline, and you just follow your outline step by step. So the first thing that we're going to do is we're going to construct a perpendicular line from B to AC. Okay, so that's going to be a perpendicular line, so that this line B, I'm going to call it BM. BM is going to be perpendicular on AC. So now you should see three triangles. We have a triangle AMB, and we have a triangle BMC, and we have a big triangle ABC. You see that? Okay. So the first thing I'm going to do is I'm going to show that triangle AMB is similar. Now, to show something is similar, we use three lines like that. I'm going to show it similar to the big triangle, which is triangle. Now, again, the angles must line up. Okay, so in AMB, I'm going to show it similar to the big triangle. So obviously, angle A and angle A is the same angle. So this one will also be A. This one's 90-degree angle is angle M. The big one is angle B. And the last angle, for this one, it will be 1. Okay, that's the angle left, and for this one, angle C is left. So angle AMB is congruent to angle ABC. Not congruent, similar. The reason why I'll do that is what I'm going to do is I'm going to find an expression for AB squared. And how I will find that expression for AB squared is I'll have AB over something is equal to something over AB. And then when I multiply both sides with AB, I will get AB squared on this side, and on this side I will have something times, I'll multiply this on that side as well. Okay, so but I'll get an expression for AB squared. That's the first thing. This is kind of the first aim, to get an expression for this. Secondly, I will get an expression, or I'll show that triangle, and now I'm in this triangle, BMC is similar to triangle, okay, so BMC, this time I'm again trying to show that it's similar to the big triangle. So again, C is corresponding, so my last angle is clearly the one that is easily shown to be equal. M is still in the middle because BMC, sorry, M is in the middle for this one, so, and that's a 90 degree, and B is the 90 degree, and then the one remaining is B2, which will be equal to A. Okay, that one is more difficult to show. And again, this time I will get I will show that BC squared, I will get an expression for BC squared. And then, so that's the second thing I'm going to do, is show that these two are similar, and from that similarity I'll find an expression for BC squared. Same idea. And then the last thing I'll do is I will add the two expressions that I get, AB squared plus BC squared, and I will just do some arithmetic, some math magic, and I'll get that that's equal to AC squared. Okay, so that's the outline. You can see again, it's not a lot. Okay, and it's the same thing twice, but it is a lot of work. Okay, so let's get started immediately so that this is not another half an hour video. Okay, so first in triangle, oh sorry, I must write down my construction first. I haven't written that. And my to prove. So to prove, I want to prove that AB squared plus BC squared is equal to AC squared. Then my construction. Okay, we said we are constructing BM perpendicular to AC. Okay, so far so good. Okay, now the first thing I want to do is now show that I want to show this. Okay, so I want to show that in triangle AMB and triangle ABC, the first one, okay, so what are the first angles that I can show? Because all I need to do is show three angles equal, and then they will be similar.
Angle that M is equal to B is equal to B.
Okay, so angle AMB is equal to 90 degrees. Why is angle AMB equal to 90 degrees?
Because it's perpendicular to AC.
Yeah, but why is it perpendicular? Guys keep getting this one wrong.
It's perpendicular because.
Why is BM perpendicular to AC? Do it in a bit darker. Was it given like that?
No.
Exactly. We constructed it. From construction. Okay. And angle B is also equal to 90 degrees. Angle A, B, C, I mean. Okay, why is angle ABC 90? That was given. We are working with a right angle triangle. That means, therefore, that angle AMB is equal to ABC. Okay, that's the first angle. Second angle, which other angle can we show is equal? Say again?
BAM equals to BAC.
BAM is equal to BAC. Why?
Yeah. It's given.
It's not given.
It's right there.
It's not even right there. It's a common angle. It's the same angle. It's the same angle. So in other words, you can simply say angle A is equal to angle A. Because there's not more than one A, so you don't need to use the BAC, MAC thing. You can just say angle A is, in other words, look there, A is equal to A. Why? Same angle. Now, technically, I think that should be sufficient to show a thing is similar, because if two angles are the same, the third angle must be the same, because the angle should add up to 180. Does that make sense? Okay, but okay, it's probably good that we can show that. Anyway, I'll do this one for you so that you can do the next one. Okay, angle, which one is left? ACB. Angle ACB is equal to, so look here, angle ACB is equal to 180 degrees minus 90 degrees minus A. So this angle here is 180 degrees minus the other two. Isn't that true?
Yes.
And the other two is a 90 degrees in A. So angle ACB is 180 degrees minus 90 degrees, because the one angle is 90 degrees, minus angle A. And the reason why is interior angles of triangle. Okay, and this, if I simplify this, that just means it's 90 degrees minus A. Agreed? Okay, the other one, if I now look at this angle that I'm also working with, apparently this triangle and that this angle and that angle is equal. Okay, well, what is this angle? This angle is 180 degrees minus this angle and minus that angle, which is just 180 minus 90 minus A. So triangle ABM is equal to 180 degrees minus 90 degrees minus A, which is just 90 degrees minus A. Same reason, interior angles of triangle. Okay, and there we can see we get the same formula for both angles. Therefore, angle ACB should equal angle ABM. And that means we have shown that triangle AMB is similar to triangle ABC. The reason we showed angles. Make sense? Okay, so that was the first half of the first part.
Half of the first.
Yeah, and there's 3 parts. Okay, so the next is going to go quicker. Okay, since we know they are similar, remember we can now use this ratio. Okay, and I said I want a formula with AB in, because I want to get a formula for AB squared. So I want AB squared. That means I have to have AB over something is equal to something over AB, because I want to multiply both sides to get that AB squared. Okay, so that's what I know I want to get. So AB in the in the small triangle. So AB in the small triangle, you see it's the hypotenuse. In the small triangle, it's the hypotenuse because it's opposite the 90 degrees. So if I have the hypotenuse, okay, I can divide with the hypotenuse of the big one. Okay, or if I have this one on top, I have the hypotenuse on top on this side, I must have the hypotenuse on top on that side. Now the hypotenuse of the bigger one is AC. So I get AC. Now this is now the bigger one's side. This is the smaller one, and that's the bigger one. So the bigger one has the hypotenuse divided by something. Let's see what it is. It has the hypotenuse divided by AB. Okay, the shorter side of the two sides. So in this one, which one is the shorter side? So in the smaller one, I must also use the shorter side of the two. Which one is shorter? AM. So if I have the hypotenuse divided by the longer side of the two right sides, I must use the hypotenuse divided by the longer side of the smaller one, AM. But you'll notice here as well, look, I'm using AB, the first and the last, the first and the last. And then I'm using AM, which is the first two, and I'm using AB, which is the first two. You see, as long as you've got the order correct here, you can't mess up here. Any combination you make of these letters, as long as you keep the order. Okay, cool. Now I just multiply both sides with the denominators. Okay, so I'm going to multiply with an AB, and I'm going to multiply with AM. So AM times AB. So the AM's cancel and the AB's cancel, so that I have AB times AB, that gives me AB squared is equal to AC times AM. Okay. That's basically the first half complete. But the next half is exactly the same. Exactly. The only difference is I'm just using this triangle instead of that smaller triangle. Okay, so I'll quickly go through that. Okay, so in triangle, now I'm using triangle BMC and triangle, okay, so I have to have B is going to be equal to A, and triangle ABC. The first thing I'm going to do is just show the obvious angles that are equal. So which is the obvious angles? Well, here's the big one and here's the small one. Both of them have C as an angle. Does that make, can you see it? In the big one, ABC, I've got angle C, and in the smaller one, BMC, I've got the same angle C. You get that? So my first one would just be that angle C is equal to angle C. Same angle. The second one would just be the other easy one. Is a 90-degree angle here. So BMC is 90. Why is BMC 90 again? Please get it this time. Construction. There we go. BM is constructed on AC. Okay. So in that one, so that's the second one. BM is equal to 90 degrees by construction. By construction. While, sorry, not BM, it's BMC. While ABC is also equal to 90 degrees, that was given. Therefore, BMC is equal to ABC. And that is just a conclusion since both of them equal 90 degrees. Okay, so I've got two angles so far, the third angle. Now, in the same way, I just need to show that this last angle here, angle B, is equal to angle A. Okay, So that angle B is MBC. MBC is the last angle left, MBC, which means I can take 180 degrees and subtract these two angles. Make sense? Which is 90 degrees minus C, which is, if I simplify it, that's just 90 minus C. And why could I do that? Because the interior angles of triangle. And similarly, that's now for MBC. In other words, this angle here. Similarly, I can get the A for the big triangle by doing the same. I just take 180 minus this 90 minus this C. Okay? So triangle, what is that? BAC is 180 degrees minus the 90 minus the C is also just 90 degrees minus C. You can see it's just a repeat of what we've done so far. Okay, therefore MBC is equal to BAC. So we've shown that we have three angles that are equal. That means that triangle BMC is similar to triangle ABC. And from this congruence, I never said this, we do this from similarity. We were allowed similarity. We were allowed to say that these proportions exist because they are similar. Okay. Now, in the same way that we found a formula for AB squared, we now want to find a formula for BC squared. So we take BC divided by is equal to divided by something is equal to something divided by BC. Remember, we want that BC squared. Okay. So look, now I'm not even going to look at the sketch. I'm just going to take, at the top, I'm taking the first and the last. So here I must take the first and the last. AC. In the bottom, I used BC, the last two, so in the bottom on the other side, I must use the last two MC. Yeah, look, I used BC. This is this side, and this is this side. Yeah, but I'm not trying to get AC again. Look, I'm trying to get a formula for BC. So I know that this one must have a BC at the top, and not a formula for BC. I'm trying to find a formula for BC squared. So BC over something is equal to something over BC, so that when I multiply with BC on both sides, I will have a BC squared. Okay? But now to fill in the rest, I must use, okay, BC for the first one is the first and the last. So on this side, I must use the first and the last, which is AC. BC on this side is the last two. So I must use the last two on this side in the denominator. Make sense? And now I multiply with the denominators on both sides. So that on this side MC cancels, on this side BC cancels. So I have BC squared is equal to AC. Excellent. And now all that remains to do is to add the first and the last equation. So I'm just going to add 1 plus 2 because I want to see what is AB squared plus BC squared. Now for AB squared, I got this expression, AC times AM, AC times AM, And for BC, I got AC times MC. Now you'll notice that I have two terms. Both of the terms have an AC in, so I take it out as a common factor. And you'll see why in just a minute, because what I'm left with inside the bracket is AM plus MC. Now if we go back to our sketch, you'll see that AM plus MC is equal to what? It's equal to AC, the hypotenuse. And that is why I get AM plus MC is equal to AC. And so I get AC squared.
A.